So because this is a pure frequency component at frequency omega naught, therefore, not surprisingly, the spectrum gives you a single delta function at this frequency omega naught, okay, scaled by 2 pi. So in the discrete time case, it is the same as well, okay? So the Fourier transform is 2 pi delta omega minus omega naught, okay? The only difference is that in the discrete time case, the spectrum is periodic with period 2 pi. So not only do we have a delta at omega naught, actually we should also have one at every integer multiple of 2 pi away from omega naught, okay? So this is what you get, right? You get a delta at omega naught, and then you repeat this at every integer multiple of 2 pi. Okay. Now, how do I check if this is true or not? Okay. So we can try to plug this into the Fourier transform pair to see if it holds, right? So doing it in this direction is a little bit more complicated. So we do it in the reverse direction, right? We check with the inverse Fourier transform. So if you take the inverse Fourier transform of this spectrum, right, by definition, it's 1 over 2 pi, the integral of capital X times e to the j omega n d omega over a 2 pi range. Okay. Now this x, I substitute with this, pulse train. Okay, I substitute this inside. So I'm basically, integrating over this pulse train, right, times e to the j omega n over a frequency of 2 pi range. Okay, so any 2 pi range is okay. But if I integrate over a 2 pi range, no matter how I shift, right, I'm always going to cover one of the delta functions, okay? So suppose I cover this rth replica, right? So suppose this is omega naught plus 2 pi r, okay? So suppose that I picked a 2 pi range. I picked a 2 pi range that covers the rth delta function, okay? So then when you take the integral, you will only have a delta function at omega naught plus 2 pi r, okay? So then this will be equal to e to the j omega naught plus 2 pi r times n, okay? And this is for some r. Okay. And since both r and n are integers, therefore, omega naught n plus a integer multiple of 2 pi, is equal to e to the j omega naught n. Okay? So here we showed that, yes, this is indeed the spectrum for this complex exponential. Okay. Now, once we have the Fourier transform for this complex exponential, we then know how to deal with periodic signals. Okay? Because for periodic signals, we can always write it in terms of its Fourier series representation, which is just a linear combination of these complex exponentials. Okay? So suppose xn is periodic with period capital N, then you can write it as a linear combination of these capital N harmonically related complex exponentials. All right. So then what is the Fourier transform of this? Okay. So the key idea here is that the Fourier transform we can then write as a linear combination of the Fourier transform of each one of these. Okay. So x times e to the j omega is equal to summation ak, right, summed over n, capital N consecutive integers times summation L from minus infinity to infinity 2 pi delta omega minus 2 pi k over n minus 2 pi L. Okay? So this is just the Fourier transform of this complex exponential, right? Now let's just exchange the order of the summation. So here I'm just exchanging the order of integration and combining these two terms, right? So I have 2 pi over capital N times k plus L capital N. Okay. Now here we have k that is summed over capital N consecutive values, okay? So any consecutive capital N values can do. So let's pick a particular value. Let's sum specifically from 1 up to capital N. Okay? And suppose we do a change of variable where we set k prime equal to k plus L n. So in this case, we get L summation over L 2 pi summation over k prime, which now goes from L capital N plus 1 up to L plus 1 capital N, a k prime minus Ln delta omega minus 2 pi over capital N k prime. Okay? So I'm doing a change of variable where I set k prime equal to k plus Ln. Okay? So now, instead of for k from 1 to capital N, I now have k prime from 1 plus L capital N up to capital N plus L times capital N. Okay? And k becomes k prime minus Ln, and k plus Ln now is k prime. Okay. Now the key idea here is that, the key thing here is that we know from before that the Fourier series representation for discrete time signals must be periodic. Okay? So the Fourier series coefficients here are periodic. This is a k prime minus Ln equal to a k prime for all integers L. Okay? So you can just view this as AK prime, okay, as AK prime. So now we have K prime summed from Ln plus 1 to Ln plus capital N, okay? So this is over capital N consecutive values. But then as you further sum L from minus infinity to infinity, right, then you go from Ln plus 1 to L plus 1n, and then you have L plus 1n plus 1 to L plus 2n, and so on and so forth, right? You cover these blocks consecutively, so if you span them out, you are essentially summing over all values of K prime, okay? So this is the summation of k prime from minus infinity to infinity of 2 pi a k prime delta omega minus 2 pi over n k prime. Okay. So this is the Fourier transform of a periodic signal with Fourier series representation given by this. Okay? All right. So let's look at a few examples. Oh, okay. So you can actually try to visualize this as well, right? So each one of these complex exponentials give you a pulse train, right? Okay. So each one of these complex exponentials give you a pulse train, right, with the impulse at omega naught and every integer multiple of 2 pi. Okay. So for every one of these, you get one of these pulse trains. Okay. So for example, for k equal to 0, right? For k equal to 0, you get this. For k equal to 1, you get this, right? For k equal to 0, you have a delta at frequency 0, but then also at every integer multiple 2 pi. Right? For k equal to 1, you have a delta function at 2 pi over capital N, and then also every integer multiple of 2 pi, okay, and so on and so forth. So you have a total of capital N of these, right? You have a total of capital N of these, okay? So if you sum them up, okay, then you will have these delta functions spanning, spanning a 2 pi range, right? And then it is repeated every integer multiple of 2 pi. Okay? All right. Now let's look at a simple example. Okay, so this is the example of a cosine function. Okay? So this cosine omega naught n is, by Euler's relation, is just 1/2 e to the j omega naught n plus 1/2 e to the minus j omega naught n, okay, where omega naught is 2 pi over 5. So from this omega naught, you can see that this is periodic with period 5. Okay? So then what is the spectrum? Okay. So you have two complex exponentials, right? Each one gives you a separate pulse train, right? So this one gives you 2 pi delta omega minus 2 pi over 5 minus 2 pi L from minus infinity to infinity. And the second one gives you, again, summation 2 pi summation 2 pi delta omega plus 2 pi over 5 minus 2 pi L. Okay? So this complex exponential gives you a delta function at frequency 2 pi over 5, and also at every integer multiple of 2 pi away. And this delta function, this complex exponential gives you a delta function at frequency minus 2 pi over 5, and also every, integer multiple of 2 pi away. okay? So if you add these two together, this is what you get, right? So this is omega naught. So this gives you this delta function, and this delta function, okay? So this term here gives you these delta functions, okay? And this term here gives you these delta functions. Okay. Now you can actually combine them together to write it more concisely using this AK delta omega minus 2 pi k over 5, where AK is equal to 1/2 when k is equal to 1 plus minus, I'm sorry, okay, 1 plus I should say plus minus 1 plus 5L for all integers L and 0 otherwise. Okay? So this AK, right, this AK, you have this non-zero value at plus and minus 1, and also every 5 samples away, okay, because the period is 5. All right. So we can look at another typical example. Okay. So this other typical example is this periodic impulse train. Okay. So suppose we have a signal that is this impulse that is repeated every integer multiple of capital N. Okay. So for this signal, we can find the Fourier series representation, and the Fourier series coefficient for this, right, if you recall, should just be a constant. Okay. So the Fourier series coefficient AK is 1 over n summation n over a period xn e to the minus jk 2 pi over capital N n. Okay? So this is summing over one period. So suppose you sum over a period covering n equal to 0, then what you have here is just 1 over n. Okay? And this holds for all k. Okay. So if AK is equal to 1 over n for all k, therefore if you plug this, okay, back into this equation here, okay, then what you have is the spectrum x, that is 2 pi over capital N summation delta omega minus 2 pi k over n. Okay? All right, so what does this tell you? This tells you that if you have a periodic impulse train in the time domain, then you will also have a periodic impulse train in the frequency domain. Okay? So if the periodic impulse train is separated by capital N, right, the period is capital N, then in the frequency domain, these impulses are separated by 2 pi over capital N. Okay? So if you increase capital N, right, if you separate the two impulses, then you will have, closer and closer samples in the frequency domain, and vice versa if you reduce capital N. Okay? All right. Okay. So all of these examples, we had something similar in the continuous time case. Okay, so we just, you can compare between the two to see if you can, gain further insights from this. Okay. Now, for the Fourier transform of the discrete time case, we can also, prove all these different properties. Okay, things like, linearity, time or frequency shifting, or things like conjugation, differencing, which is analogous to differentiation, or accumulation, which is analogous to integration in the continuous time case. Okay, so all of these properties we also have in for the discrete time Fourier transform. Okay, now one thing that is special for discrete time Fourier transform is this periodicity. Okay. So this is something that the continuous time case does not have. Okay. So we showed previously that for this discrete time Fourier transform, the spectrum must be periodic with period 2 pi. Okay. Right. So linearity is straightforward, right? If you have x1 and x2 with spectrum capital X1 and capital X2, then linear combination in the time domain corresponds to the same linear combination in the frequency domain. So time and frequency shifting is also the same as in the continuous time case. If you have a time shift, then this corresponds to a phase shift in the frequency domain. Similarly, if you have a frequency shift, then this will correspond to a phase shift in the time domain. Okay, so here is just a simple example. Suppose that you have this ideal low-pass filter, which has a spectrum that looks like this. Okay, so for an ideal low-pass filter, we want to let through signals at low frequency and eliminate all signals at high frequency. Okay, and this is again periodic with period 2 pi. Now, if you take a frequency shift, okay, if you take a frequency shift of this low pass by pi, then you will be moving this to high frequency, okay? So if you perform a frequency shift of this low pass filter by pi, then what you get is actually something like this, and this is an ideal high pass filter, okay? So in discrete time, by just shifting the frequency of the low pass by pi, you effectively get an ideal high pass filter. So the impulse response of this high pass filter in the time domain is just the impulse response of the low pass filter times this phase shift. Okay? Okay. All right. So this is actually quite intuitive as well because, suppose that this low pass, this HLP is something that is low pass, right? It contains mostly low frequency components. So this signal in the time domain should be relatively smooth, okay? But if you multiply by e to the j pi n, right, you can see that when n is 0, this is 1, right? When n is 1, this becomes minus 1, okay? So e to the j pi is actually minus 1. So what you have here is essentially minus 1 to the power n. Okay. So this low pass originally is something smooth, but now when you multiply by this minus 1 to the power n, it starts to oscillate between plus and minus really fast, okay? So it turns from a low pass to something that is high frequency dominant.